Okay, so last week we studied what's called linear homogeneous recurrence relation. This is a specific case of linear recurrence relation with no constant term. So this was a general form of linear homogeneous recurrence relation where C1, C2 to Ck are just a fixed constants. And you know that the next term an depends on the previous k terms, an minus 1 to an minus k. So that if you specify the first k terms, then you can use this recursion to compute a k plus 1. And then you can reuse these k terms from a2 to k plus 1 to compute the next term, k plus 2, and so on and so on and so forth. So what you have to do is just to specify the initial condition, which are the first k terms of the sequence, to obtain the unique solution of this linear homogeneous recurrence relation. And also, I explained that some solutions of this homogeneous recurrence relation have the form of R to the k. So we guess that this is a solution for this linear homogeneous recurrence relation for some R. And if you plug in this equation into this recurrence relation, then we obtained this polynomial with respect to the variable R. So just by dividing this equation by R to the n minus k, power of n minus k, we obtained the polynomial which was called the characteristic equation, which is a polynomial of degree k of variable R. And last time I didn't explain this part very precisely, but intuitively you can say that you will learn the formal definition about dimension or vector space in linear algebra, but you can still get some intuition here. So you can basically choose any initial values from A1 to AK to construct a solution for this linear homogeneous recurrence relation of degree k. So intuition in here is that basically the solution space has the dimension of k, roughly speaking. So you don't have to know the definition, formal definition of dimension here, but just roughly speaking, you can say this solution space has dimension k. So that what we have to do is to find, our goal is to find k independent solutions. Because if we find k independent solutions, so I'm not going to define the independency of solutions formally here, but if you can find k independent solutions, you can basically mix them. Mix means you can take their linear combinations to express any initial condition of the first k terms. Meaning that if you find k linearly independent solutions, then arbitrary solution of this linear homogeneous recurrence relation can be represented as a linear combination of these k independent solutions. So that's why we basically try to find, for example, two independent solutions in the case of degree 2. So recall that if our recursion is the form of an equals c1 an minus 1 plus c2 an minus 2, meaning that the characteristic equation of this linear recurrence relation is obtained as this degree 2 polynomial. And we also check that this sequence a over n, which is defined by r to the power of n, is a solution of this linear recurrence sequence if and only if this R is a root of this characteristic equation. So in other words, if this if this characteristic equation has two distinct solutions, let's say R1 and R2, then we obtained two independent solutions, which are R1 to the power of n and R to the power of n. So these two were two different solutions, and they were independent solutions of this linear equation, so that we could take linear combination of two solutions to represent arbitrary solution of this linear equation. That's what we studied last week. And this was a concrete example, Fibonacci numbers. And we stopped here. So last time I asked this question that this slide was about the case where this characteristic equation has one repeated root, meaning that this quadratic polynomial has only one root, which is R0, but its multiplicity is 2. So we can represent characteristic equation as the square of R minus R0. In this case, of course, this sequence of R0 to the power of n can be a solution of this sequence, but we don't have the second solution. So we should find the second solution, which is independent to this basic solution. And I mentioned that if a polynomial, so if this polynomial has one repeated root R0, then let me write this as well. So we knew that this is 0, and we also knew that its derivative has the same root R0 because we have this multiplicity 2 here. And recall that we were motivated from this polynomial actually. So R to the n minus C1. So R0 is also a solution of this polynomial of degree n, and also has multiplicity of 2. So if we take a derivative of this polynomial, then we obtain this equation, and we know that R0 is a root of this polynomial because it has multiplicity of 2. And that's why we know that this n times R0 to the power of n is another solution of this recurrence relation, because if you just plug in this R0 into this equation and just multiply R0 on both sides, then you obtain n times R0 and 1. You obtain this equation. So you can see that if you define an as n times R0 to the power of n, then this is an minus 1 and this is an minus 2. So this sequence of n times R0 to the power of n is a solution of this linear recurrence relation. So now we found two solutions of this recurrence relation, which are R0 to the power of n and n times R0 to the power of n. And you can just simply check that these two solutions are linearly independent, meaning that you can combine these two solutions to express any initial condition. So meaning that this is the first solution you have, and this is a second solution you have. So if n is 1, n is 2, then you have R0 square, and R0 2 times R0 squared. And for any A0 and A1 you get, you can already find some alpha 1, alpha 2, such that alpha 1 times R0 squared plus alpha 2 equals, sorry, this should be A1 and A2. Because these two vectors are linearly independent. So you can already find such an alpha 1 and alpha 2 satisfying this linear equation. So this is what exactly this theorem claims, because in this theorem it says that if an is this theorem basically claims two things. First, it claims that this R0 to the power of n and n times R0 to the power of n are two solutions of this linear recurrence relation. And secondly, if the sequence is a solution of this recurrence relation, then this solution can be already represented as a linear combination of these two basic solutions. And it is already possible to find such an alpha 1 and alpha 2 because these two solutions are linearly independent. So here's one example of this case. So suppose that we are looking for a solution of this linear recursion with the initial condition this and this. And its characteristic equation has only one root, which is 3. So that we know that two basic solutions of this linear recurrence relation is obtained by 3 to the n and n times 3 to the n. And what you now have to do is to find these constants alpha 1 and alpha 2. And this can be done by simply checking the initial conditions, just putting 0 and 1 to n, and you can simply compute alpha 1 and alpha 2. So even if you change these initial conditions, you can already find some good linear combination coefficients alpha 1 and alpha 2, so that the solution has satisfy these initial conditions. So this is a more very general theorem about linear homogeneous difference relation. So it looks much more complicated, but it has exactly the same intuition. So just looks more complicated, but nothing special. So suppose that now you're working on the general linear homogeneous recurrence relation of degree k. So the characteristic of equation is obtained as this phi of r is obtained as this polynomial of characteristic of degree k. And suppose that this polynomial has t distinct roots r1 to rt with multiplicities m1 to mt. So meaning that this polynomial phi of r is represented by 1 to the m1 rt mt. So this r1 to rt are distinct roots of this polynomial, and ri has the multiplicity of mi. So that the summation of this multiplicity should be equal to the k, which is the degree of this polynomial. Make sense? So, so that since R1, R2, RT are solutions or roots of this characteristic equation, we know that R1 to the n, R2 to the n, RT to the n, power of n, they are solutions of this linear recurrence relation. And secondly, if some of them have a multiplicity larger than 1, okay, so let's take this R1 as an example. Suppose that M1 is greater than 1, then we know that its first derivative has R1 as a root because its multiplicity is n is to 2. And we know that phi over its m1 minus 1 derivation of this polynomial has this R1 as a root. So meaning that for example, let's say for example, if M1 is 3, then we know that this is true and this is also true. And now you can see that there are M1 independent solutions given in this theorem. So alpha i's, alpha ij, they are just a question. So you can just ignore them when you read this theorem. So this theorem basically says that the first solution of this recurrence relation is simply R1 to the power of n. And the second solution is obtained by n times R1 to the power of n. And the third solution is obtained by n squared times R1 to the n until n to the power of m1 minus 1 times R1 to the power of n. So this theorem basically says that these are solutions for this linear recurrence relation. And the reason is that the reason is just obvious from this condition, since the first derivative of this characteristic equation has R1 as root, this becomes a solution because if you take we already saw this in the previous slide. So since they satisfy so since R1 is a solution of this, if you take a first derivative, then you obtain k minus 1, and I1 is a solution for this polynomial. So if you just multiply, if you put I1 inside this polynomial and multiply I1, then you can check that this is a solution for this linear recurrence relation. And if you take one more derivative, then you obtain n times n minus 1 in front of this polynomial. But since this is already solution for this one, this recurrence relation, you can also deduce that n squared r1 to the power of n becomes another solution for this recurrence relation. So you can just repeat this argument m1 times to deduce that this m1 solution, m1 number of sequences are different solutions for this linear recurrence relation. So this is just a simple arithmetic. So you can just try to check that these are solutions for this linear recurrence relation, because from these conditions about derivative of characteristic polynomial, and the same argument can be made for other roots R1, R2, and RT, so that you can find that in total you can find the k independent solutions for this linear recurrence relation. So to sum up, this theorem says that there are k linearly independent solutions which are R1 to the power of n, n times R1 to the n to the power of this one, n, R2 n, so there are k many independent solutions, and these are all solutions. They are solutions over this linear recurrence relation. And then the second claim is that any solution over this recurrence relation can be represented as a linear combination of these k solutions. So this is what this theorem says. So this equation just looks complicated, but the behind the intuition is not very different from these basic theorems for degree 2. So you can just spend some more time to understand the message of this theorem. Okay, so that's the end of linear homogeneous recurrence relation. And in the next subsection is about non-homogeneous recurrence relation. So a linear recurrence relation is called a non-homogeneous recurrence relation when it has some additional factor f of n in the recurrence relation. So basically, this recurrence relation was called homogeneous when we don't have this extra term, but it is called non-homogeneous when we have this extra term over f of n as a constant. So this is a non-homogeneous case, is a more general case of homogeneous recurrence relation. And we say that this recurrence relation without this function f of n is called associative homogeneous recurrence relation. So for example, this is a example of non-homogeneous recurrence relation, and its associative homogeneous recurrence relation is simply an equals an minus 1. And this is another non-homogeneous recurrence relation, and its associative homogeneous recurrence relation is this. which is the same relation as the Fibonacci numbers. And this explains a general approach how we can solve the non-homogeneous recurrence relation with this constant question. So we say that Pn is called a particular solution of this linear equation if it just satisfies this relation. So any solution of this non-homogeneous linear recurrence relation can be called a particular solution. And once we find a particular solution, then any solution of this non-homogeneous linear recurrence relation can be is of the form of a Pn plus h of n, where h of n is a solution of this homogeneous recurrence relation without f of n. So roughly speaking, we already know how to solve this homogeneous recurrence relation in the previous subsection. And this theorem says that if you can find just one particular solution for this non-homogeneous linear recurrence relation, then you can just combine this particular solution and homogeneous and the general solution for this associative homogeneous recurrence relation to express any solution of this non-homogeneous linear recurrence relation. So let me just show you one example that would be better. So suppose that we are given this non-homogeneous recurrence relation. An is 3 times a of n minus 1 plus 2n. So the associated homogeneous recurrence relation is an is 3 times an minus 1. And we know how to solve this homogeneous recurrence relation. It's easy. So we know that every solution of this recurrence relation is obtained by alpha times power of 3 for some constant alpha, because each characteristic polynomial is r minus 3, so that it has just one solution 3. So the 3 to the power of n is a basic solution, and we just need to multiply any constant alpha to express any solution for this homogeneous recurrence relation. So this part is easy. Now, more challenging part is to find a particular solution for this non-homogeneous recurrence relation. And unfortunately, there's no general method to find a particular solution for non-homogeneous recurrence relation. It's just unknown how to generally find a particular solution for non-homogeneous recurrence relation. What you can do is just simply observe this form of recurrence relation and just get some solution. So this is kind of a irresponsible explanation, but that's true. There's no known method to solve this non-homogeneous recurrence relation. So since we have since this extra term f of n is 2n, we just guess that possibly the particular solution is of the form of a linear polynomial Cn plus d. So there's no logical argument made here, just a guess. It's just a guessing. We just guess that possibly this linear polynomial can be a solution for this recurrence relation, because this extra term 2n is a linear polynomial. So let's try. I mean, if you fail, then you can try another form of solution. So this is just a successful try, but if you really try to solve some non-homogeneous recurrence relation, you may need to try different types of functions until you find the correct particular solution. So now we suppose that Pn is of the form of Cn plus d, Coulson constant Cnd, and just put this our guessing into this recurrence relation, and you obtain this result. So if Pn is Cn plus d, then Pn minus 1 is C times n minus 1 plus d. And so if this Pn satisfies this recurrence relation, then you just you can just put this into this recurrence relation, Cn plus d equals 3 times and this is true for any n, if and only if C, so because this is 3C plus 2 n minus 3. So this is true for every integer n, if and only if C is and d is equal to this value. And this is given here. We just have this condition from here. So the P of n is solution of this recurrence relation if and only if C is minus 1 and D is minus 3 over 2. So consequently, we know that this P of n is a particular solution of this recurrence relation. So we conclude that every solution for this recurrence relation is the form of Hn plus Pn, where Pn is any particular solution for this recurrence relation, and H of n is a solution of this homogeneous recurrence relation, which is alpha times 3 to the power of n. So we deduced the conclusion that every solution of this recurrence relation, non-homogeneous recurrence relation, is of the form of this, where alpha is a fixed constant. So, oh, Jiun asked a very good question. So I just skip the theorem, the proof of this theorem here, but it's in fact very easy to show. So suppose that, let me just give a proof idea. Suppose that An is an arbitrary solution of this recurrence relation, and Pn is a particular solution. Then you just consider the sequence H of n, which is defined by An minus Pn. Then you can show that H of n is a solution of an associative homogeneous recurrence relation. The reason is that both An and Pn satisfy the same recurrence relation. So we know that this is true. C1 An minus 1, Ck An minus k plus f of n. And we also know that the particular solution satisfies the same non-homogeneous recurrence relation. So if you subtract this, you obtain H of n equals C1 H of n minus 1 plus Ck H of n minus k, and these terms are cancelled out. So if you find any particular solution, then for every solution A of n of this non-homogeneous linear recurrence relation, their difference H of n becomes a solution of a homogeneous recurrence relation. So in other words, every solution of this non-homogeneous linear recurrence relation can be represented as a sum of Pn and Hn. So particular solution actually means nothing. So it's just a solving strategy. Particular solution means, in general, this non-homogeneous linear recurrence relation has infinitely many different solutions. But this theorem says that what you need to do is find just one solution, any. So that one solution is just called a particular solution. So it's just one of the solutions of this non-homogeneous linear recurrence relation, which doesn't have to have any special condition. But yes, just one of the solutions. That's it. So as you can see here, there are infinitely many different solutions of this same recurrence relation, but you just found one solution. But this is not just a unique particular solution. If you somehow able to find, I would say, Q of n, which is 3 to the n. Suppose that you somehow found this particular solution, because this is also a solution of this non-homogeneous recurrence relation. And there's no problem at all. If you somehow found this solution, then this Q of n can be played as a particular solution in this theorem. But still, the final conclusion is the same, because anyway, you will conclude that your any solution Pn is a sum of this different particular solution and solution of a homogeneous equation. So you will write this as a conclusion, but this form and this form has no difference. They are just they just represent the same set of solutions in a different way. So if you put alpha 0 here, then it's equivalent to the case where alpha is 1 here. So they are the same representation of the same solution space. Okay, so this was a very difficult part, but I believe many of you can at least get some idea about how to solve the linear equation. And in fact, this high-level strategy of solving recurrence relation is reused when you're solving some general differential equation. So like a partial differential equation or some continuous mathematics. In differential equation, you also find some homogeneous, some solutions of a homogeneous differential equation, and find one particular solution of a differential equation, and there some can represent every solution of a differential equation, satisfying some initial condition. Okay. So is it? I got another question. Hn is a complementary. What does complementary mean exactly? I don't think I understood your question. Okay, let me just move on for now. So you recall that we earlier studied one algorithmic paradigm. So this section is now about back to algorithms. So earlier we studied, I mentioned that there are some algorithmic paradigms, and one of them was called brute force algorithm. So brute force algorithms didn't use any special idea to solve a specific problem, but they just tried all possible cases until finding a correct solution. But today we study some more interesting paradigms. The first one is called dynamic programming. And second one is called divide and conquer. Yeah, they look very similar, but there's some difference between dynamic programming and divide and conquer. So this dynamic programming, this term was this is basically named by mathematician Richard Feynman in 1950s. There's some interesting historical stories about its naming. So you can just search for the term dynamic programming on Wikipedia and read some stories. So at the time, he wanted to get some funding from some government institute, but he heard that that institute didn't like some terms like mathematics or research. So he tried to find some good naming to hire the probability of getting budget from such a government institute. So he thought maybe this dynamic programming doesn't sound like a mathematical term, and it sounds like very practical research project. So he just decided to use this dynamic programming. But in fact, it represents the nature of this dynamic programming very well. So I think this sounds reasonable. So this, okay, let's get back to definition. So an algorithm for computational problem is called to follow the dynamic programming paradigm. When this algorithm breaks down a problem into simpler or smaller sub-problems, but these simpler or smaller sub-problems can be overlapped. So this overlap, I will explain about this overlap, the term overlapping again very soon. And then now this a problem is broken down into a smaller or simpler sub-problems so that we can compute the solution of these sub-problems more easily. And then later, we can use some recurrence relation or some other facts to combine these solutions of sub-problems to obtain the solution of this original problem, large problem. So roughly speaking, you just break large problem down into smaller problems and solve these smaller problems and then combine their solutions of sub-problems to obtain the solution for large problem. And this overall strategy looks very similar to the divide and conquer algorithm paradigm. But in the case of divide and conquer algorithmic paradigm, it recursively divides the problem into sub-problems. But in this case, these sub-problems should be non-overlapped. So they should be somehow independent. And in the case of this divide conquer, we just solve these sub-problems. They are non-overlapped. They are not overlapping. And then we combine the solutions of these sub-problems to obtain the solution of the original problem. And I will just introduce only one example of dynamic programming in this lecture, but possibly you'll have a chance to study some more algorithms in this dynamic programming paradigm in the homework, maybe. So recall that we already studied this scheduling problem in earlier section. Let me just record the description of this problem. So suppose that we have a collection of some proposed talks, invited talks, with starting and ending times. So, and we have only one lecture hall, so that once a talk starts, then it continues until it ends, and no two talks can proceed at the same time. So this is a basic setting of a scheduling problem. And in chapter 3, we studied the greedy algorithm. So that, in chapter 3, our goal was to schedule as many as talks possible in a lecture hall. So we are given some schedules of these proposed talks, and our goal is to arrange as many as talks possible in a single lecture hall. But now our goal in this slide is different. Now suppose that our goal is not to schedule the most talks possible, but our goal is to have the largest possible combined attendance of the scheduled talks. That's the difference. So it's a more complicated setting. So this is a formalization of this problem. So suppose that we have n talks. Let's say there are talks 1 to n. There are n talks. Each talks have a starting and ending time. So talk j begins at time tj and ends at time ej. So talk j is something like this is a starting time and ending time. And of course, we also have a number of attendees. Wj is a number of attendance of the talk j. So this is the description of the problem. And now our goal is to schedule, arrange a subset of these n talks to maximize the sum of wj, which is the number of attendees of all scheduled talks. So meaning that if the same student attends more than one talk, then we count this student multiple times so that the same student can be counted according to the number of talks attended. So make sense so far? So do you remember how we solved this easier problem? How did we arrange as many as talks? So in this easier problem, we sorted this n proposed talks with respect to their ending time. And then we just arranged the talk one by one, depending on their ending time. So we first chose the talk with the earliest ending time, and then looked at other compatible talks which end earliest at the earliest time. So we used the Discrete algorithm to find the schedule with the maximal number of talks. But in this case, we are trying to maximize the total number of student attendees. So our strategy should be changed. So this is a solution. So this part is the same. So that we first sort the talks with respect to their end time, so that this end time is increasing. So then we have n talks with end time E1, E2, En, which is increasing. And we also say that two talks are compatible if they can be part of the same schedule. So meaning that their schedule is not overlapping. So if the time stay schedule is not overlap. So this is just one example case. Suppose that we have 7 talks. Then you can see that talk 1 and 2 are not compatible since their schedule is overlapped. But you can see that, for example, talk 1 and 3 are compatible because talk 3, the start time of talk 3 is later than the end time of talk 1. So you can arrange talk 1, talk 3 in the same lecture 4. So we use this the notion of compatibility. And in the meantime, we also define a function p of j for 1 to j. So here pj is an index I such that I should be first smaller than j, and then ei should be equal to or less than sj. And we choose I, largest I among indexes I satisfying this condition. So in other words, so this talk p of j is talk ending latest among the talks compatible with talk j that ends before before talk j ends. So meaning that so we are basically looking for largest index such that I among the talks I which is compatible with the talk j. So let's just take a look at example. And we also define p of j as 0 if there are no such talks. So p of 1 is obviously 0 because in this case j is 1. So there's no I which is smaller than j. So we define p of 1 as 0. But for example, let's p of 3 is 1 because when you compute p3, you just need to check if talk 1 and talk 2 are compatible with talk 3 or not. And among these previous talks, you just find the largest index integer I such that talk I is compatible with talk 3. So you can see that talk 2 is not compatible with talk 3 because they are overlapped, but the talk 1 is compatible with talk 3. So that's why p of 3 is 1, which is this 1 is 1 of talk 1. And when you compute talk 4, p of 4, you focus on talk 4 and then check if any of the previous talks are compatible with this talk 4. And you can see that talk 3, talk 1, 2, 3 are not compatible with talk 4. So the p of 4 is 0 because there's no talk I smaller than 4 which is compatible with talk 4. And the same argument is made for talk 5. And if you now let's take a look at talk 6. When you compute p of 6, now you just look at previous talks, talk 1, 2, 3, 4, 5, and check which of which are compatible with talk 6. You know that talk 5 is not compatible, talk 4 is not compatible, 3 is not compatible, but 2 is compatible, right? And talk 1 is also compatible with talk 6, but the definition of pj is the largest integer I among these compatible talks. So that's why p of 6 is 2, because talk 2 is compatible with talk 6. And finally, when you compute p7, you know that 6, 5 are not compatible with 7, but this talk 4 is compatible with p7. So the p of 7 is 4. So is it clear, the definition of p of j? Okay. Was there a typo? You mean I think, yeah, I don't know where the typo is, but yeah, there's no SJ. So if there's a SJ, then there should be a typo. Okay, so this is typo. So this is a TJ. Yeah. So this is a idea of the solution of this scheduling problem. So so our goal. So since this is a dynamic programming algorithm, we are going to define some sub-problems, and we will solve these sub-problems one by one, and then use this, combine the solutions of sub-problems to construct a solution of the whole problem. So here, suppose that we denote Tj by the maximum number of total attendees for an optimal schedule from the first J talk. So meaning that we just consider many sub-problems so that T1 is the solution answer for the same problem with just talk 1. And T2 is the maximum number of attendees we can schedule for talks 1 and 2, and so on and so forth. And the T of n is the maximum number of the total attendees for an optimal schedule for all talks 1 to the n. And of course, it's obvious that this is increasing because if we have more talks, then we have more chance to have a schedule these talks for more attendees. So our goal is to finally find this value of T of n, but what you're going to do is to find all values of this T1, T2 to Tn. Okay, and we are going to use some recursion. We are going to construct some recursive relation between these values T of n. So, okay. So suppose that we so what should be the value of T1 first? So this is just the W1, which is the number of attendees of talk 1, because if we have only one talk, then we can just schedule this one proposed talk with a W1 number of attendees. And now we suppose it's similar to mathematical induction. Suppose that we somehow computed T over 1 to the T over J minus 1. Now we want to compute T over J. And this slide explains how to compute this value T of J from these T values with smaller indexes. And to compute this value to J, T of J, let's consider two cases. So our goal is to find an optimal schedule of the first J talks. And there are two cases. First case is that this talk J do not, the first case is that this talk J belongs to the optimal schedule. And the second case is that this talk J does not belong to the optimal schedule. Is it clear? So the second case is more easy, is easier. So let's just look at this case 2 first. Suppose that talk J doesn't belong to an optimal schedule we want to find. Meaning that it follows that an optimal schedule from these first J talks is equivalent to an optimal schedule for the first J minus 1 talks in the second case, because the talk J is not going to be part of the schedule. So that we know that in this case, T of J is equal to T of J minus 1, because it's exactly the same problem as the J minus 1 case, the case of J minus 1 talks. But this case 1 part is more tricky. But if suppose that talk J is included in this optimal schedule, then we know that these talks P of j plus 1 to j minus 1 do not belong to this schedule. So the record that the definition of Pj is that this P of 6 was 2, for example. P of 6 was 2 because this talk 5, 4, 3 were not compatible with talk 6, but the talk 2 was compatible with talk 6. And meaning that if talk 6 is part of an optimal schedule, then talks 3 to 5 do not belong to an optimal schedule because these talks are not compatible with talk 3. So if talk 6 is already included in the schedule, then automatically we can exclude this talk 3, 4, 5 because they are not compatible with talk 6. So, but still talk 2 can be part of optimal schedule because talk 2 is compatible with talk 6. So, and P of j exactly compute the index of this talk 2, which is compatible with talk 6. Okay. So that's why we can say that if talk j belongs to the schedule, then any talk between P of j and j cannot be part of this optimal schedule because these talks are not compatible with talk j from the definition of Pj. Okay. And then, so talk j is part of this optimal schedule. We also know that these talks from P of j plus 1 to j minus 1 do not belong to optimal schedule because they are not compatible with talk j. And now the remaining talks are talk from 1 to P of j. And so that's why now our goal is now to arrange the optimal schedule using these first Pj talks. And we know that they are compatible with talk j because we sorted these talks with respect to their ending time. So they are all compatible with talk j, they are not. So now we just need to find optimal schedule using this first P of j talks. And then the optimal schedule for first j talks are just can be obtained by finding optimal schedule for this first P of j talks and add one more talks j, add one more talk j. So that's why T of j is obtained by T of P of j plus wj because we just need to compute the maximum number of attendees for the first P of j talks, and then we just add the talk j with the wj attendees. So we find this recurrence relation. So there are two possibilities that a optimal schedule may or may not include this talk j. So that finally we combine these two case possibilities so that we obtain this recurrence relation between Tj given by this. There are two cases where optimal schedule contains j or not. And we consider these two cases and find maximal number of attendees for these two cases and choose the larger value. That's how we find the maximum number of attendees for first j talks. And this value can be computed efficiently because we suppose that we have already computed the previous values of t. So that if you know the previous values, then you can easily compute this recurrence relation. So this is just a pseudocode for dynamic programming algorithm for scheduling talks problem. And it just describe what we studied in previous slide. Just sort these talks with respect to their ending time. And the first part of pseudocode, compute pj. So compute p1, p2, p of n. This is the first part. And in the second part of pseudocode, use this value to compute t of 1 to t of n recursively. And the final output of this algorithm is t of n, which is the maximum number of attendees we can arrange using the n talks. I just brought this algorithm from the textbook, but I think this is a typo. So this initialization should be come out of a for loop. So T0 initialize as 0. Okay, so any question? Okay, we have about 4 minutes left. So I will just briefly recall the definition of divide and conquer algorithm paradigm and finish the class. So I already mentioned that divide and conquer paradigm is similar to dynamic programming, but the main difference is that in this paradigm, we divide the problem into one or more instances of the same problem of smaller size. And we solve individual problems. And then finally, we use the solutions of these individual sub-problems to find the solution of the original problem. And for example, binary search can be a good example of a divide and conquer algorithm, because in binary search, we just, our goal is to find a value x in a sequence of integers. And then what we did previously was to divide this list into two sublists, and then compare this element, middle element, with this curly x to determine if x is possibly contained in the left sublist or right sublist. So we just we start from list of length n, but after one comparison, we choose just one sublist, left or right sublist, and then now search x in the left sublist and repeat it by dividing this list into two sublists of almost equal size. So that was a good example of divide and conquer algorithm. And merge sort can be another example of divide and conquer algorithmic paradigm, because in the case of merge sort, we divided a list into two of equal size, and we sort left list and right list separately, and then finally we merged sort these two lists of size of length n over 2, and then merge these two lists to obtain a sorted list of length n. So this could be another example of divide and conquer algorithm. So in the case of this paradigm, not always, but many algorithms follow this recurrence relation about their complexity. So suppose that in the divide and conquer recurrence relation, in the case of divide and conquer algorithm, suppose that we divide a problem of size n. This size could be a parameter for a problem. For example, the length of a list, for example. Suppose that we divide a problem of size n into sub-problems, and the subproblem has the size of n over b. And suppose that now we have a we broke this problem into 8 sub-problems. So this is not all sub-problem, but this is a number of sub-problems A. And each sub-problem has the size of n over b. And we also define f of n as the extra complexity number of operations that are needed in the conquer step. So conquer means, in the case of a merging sort, for example, we split this sorting problem into 2 sub-problems, and then we sort the individual lists, but we also performed extra operation in the merge algorithm to merge this, to sort the list of length n over 2. So this is an extra operation for conquer. So this f of n denotes the complexity of these extra operations in the conquer step. Okay, then we can now define we can obtain the recurrence relation between this complexity. Here, T of n denotes the number of total operations to solve a problem of size n. And we obtain this recurrence relation. T of n is A times T of n over b plus f of n. The reason is that we broke down a problem of size n into a many problems of size n over b. So it takes T over n over b complexity to solve each problem, but there are n many such sub-problems in total. So we need this many operations to solve a many sub-problems. And we also need this extra f of n complexity in the conquer step to merge these solutions of individual problems and obtain the solution of the original problem. So that's why we often get this type of recursive relation between the complexity of the divide and conquer algorithms. Okay, so sorry, time is already over. So